Okay, so this is your first part of your Flex Unit 1. The big thing here is it appears on the ACT. You do not see this too much in college algebra or at all for series and sequences, and we don't cover everything in this unit. We don't cover infinite geometric series. We do that in Algebra 3. But basic arithmetic and geometric series and sequences do appear on the ACT, so I want to be sure and cover that. So the first thing is identifying what a sequence is, and a sequence is a set of numbers with a particular order or pattern each number is called a term. So it's a set of numbers with a particular order or pattern. Each number is called a term. So a finite sequence, notice it's not infinite. A finite sequence means that it has a limited number of terms. So a lot of students tend to think of finite as, oh, it's like 5, it's like 10. But finite just means that it is countable, but large numbers are countable. So it could have 1,000 terms, it could have 100 million terms, but it does have an end at some point. So a finite sequence is a sequence with a limited number of terms. So remember, this can span anywhere from 2 to 2 million. It just has to have an end. So for example, 1, 2, 3, 4. Finite sequence has 4 terms. Okay? An infinite sequence obviously would be a sequence with unlimited terms. So it does not end. So we do 0, 1, 2, 3, and dot, dot, dot. It is 3 dots specifically. It's actually a math notation, 3 dots. And this is the set of whole numbers. So as you know, the set of whole numbers does not stop. It continues on forever. So it is definitely an infinite sequence. Okay. So term notation, the first term in a sequence is denoted as a sub 1, as in the first term. Each subsequent term is denoted a sub n, where n is the term number in the sequence. So a sub 1, for instance, in this given sequence, a sub 1 is the first term, so that's 1. A sub 4 would be the fourth term, so 1, 2, 3, 4. This would be 13. A sub 9, now we have a problem because the 9th term isn't listed here. So we need to figure out what our pattern is. Anybody have an idea of what the pattern might be? Yeah, it's plus 4. So if I want to continue on, I need to add 4. So 17 and 4 is 21, 25, 29, 33, 37, 41, 45. So now I can find the 9th term. 1, 2, 3, 4, 5, 6, 7, 8, 9 is 33. And the last one is the 12th term. So 9, 10, 11, 12. Clearly why I stopped at 45. Okay. So you've been figuring out patterns since you were at a very young age. So probably around 4th grade, they give you this list of numbers and there's some kind of pattern. Add 1, add 2, add 3, subtract 1. You get into multiplication and then maybe it's multiply by 2 or something like that, which we will actually get to with the geometric and the arithmetic, those patterns. But you don't learn those fancy words when you're in the younger grades. You just know that you're trying to figure out the pattern and you figure out the pattern, right? So sequences as functions. So since each term value is paired with exactly one term number, a sequence is a function with the following properties. The domain is the set of term numbers. So this, like if this was a finite sequence, it has 5 terms. First term is 1, second term is 5, third term is 9, fourth term is 13, and fifth term is 17. The range would be the set of term values. Okay. So the term number is where it happens in the sequence. The term value is what that value is in the sequence. So we'd have to have the term values to figure out the pattern, right? So the term values are my pattern. The term number is just how it comes in order, okay? In an infinite set, the domain is the set of natural numbers. So remember that natural numbers or the counting numbers start with 1 and go to infinity. So they're just saying if it's an infinite set, then it's just 1 to infinity, right? Because you have infinite terms in an infinite set. So when you're starting with basic formulas, you have 2 types. The first is recursive. A recursive formula is a rule in which one or more previous terms are used to generate the next term. This is actually what you're most familiar with, because just like in this first pattern, we needed to know what this one was to figure out this one, because it's the previous term plus 4. So 1 plus 4, then 5 plus 4, 9 plus 4, and so on and so forth. That's what you're actually most familiar with, even though it's the most difficult to write. It's actually the ones you're most familiar with. The most famous or infamous, I guess, recursive formula is the Fibonacci sequence, which starts with a 0 and a 1, and then it's the sum of those. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and so on and so forth. Okay? In this sequence, a sub 1 is equal to 0, and a sub 2 is equal to 1. And then for each subsequent term, so the term that comes after is going to be the sum of the term before it, so the term before it, plus the term 2 before it. So that just means, like, if I want to know the third term, that would be 3 minus 1 plus 3 minus 2, which is just a sub 2 plus a sub 1. Sorry. And my pad is not working. Sorry. Of course it would go haywire. There we go. Now we're back. So a sub 1. So again, the term before it and the term 2 before it, which is what we did. 0 plus 1 is the third term. So the second term, plus the first term was the third term. Okay? So don't get bogged down in the notation. So examples, find the first 5 terms in each sequence. We're only going to find the first 3. If you can find the first 3, you can find the first 5, you can find the first 10. It's just a matter of doing the math. You'll do this on your homework daily grade as well. You only find the first 3 terms, not the first 5. Okay, so it says if a sub 1 is equal to 14, we want to find a sub 2 and 3. So a sub 2 would be a sub n minus 1, so 2 minus 1 plus 9. So that would be a sub one plus 9, and the value of a sub 1 is 14. So a sub 2 equals 14 plus 9. So a sub 2 is equal to 23. If I want to find a sub 3, that would be a sub 3 minus 1 plus 9. 3 minus 1 is 2. And the second term we just found is 23. And that means the third term is 23 plus 9, which is 32. So you're not going to have to show this every single solitary time. I would hope that you would get in the habit where you could say, oh, 3 minus 1 is 2 and skip right here and not have to write it out every single time. So that's what we're going to do in problem number 2. We're not going to show all of that work. Make sure you have time to finish copying. Okay, so then a sub 1 is given, so then we only have to find a sub 2 and a sub 3. So it's going to be 2 times a sub n minus 1, so the term before it, which would be a sub 1 minus 5. So 2 times a sub 1 is 6 minus 5, which means that a sub 2 is equal to 12 minus 5, which is 7. So maybe I should block those in so it's a little bit clearer. So then a sub 3 would be 2 times a sub 3 minus 1, which is 2, minus 5. So 2 times a sub 2 we just found was 7, minus 5. So that's 14 minus 5, which means that a sub 3 is equal to 9. Okay, so then they get a little more complex, but it's the same exact process. Okay, so a sub 2 would be equal to the term before it, so a sub 1 plus 6 divided by 3. A sub 1 is 354 plus 6 divided by 3, which you can plug and chug in your calculator. Be 360 divided by 3, which is 120. A sub 3 will be a sub 2 plus 6 over 3. A sub 2 is 120 plus 6 divided by 3, so that'd be 126 divided by 3, which is 42. So I don't know why all of these equal signs are so weird. But this time, we're given the first and the second term in order to find the third term. Okay, so we need the first and the second term. So this goes back to like the Fibonacci sequence where we needed the first 2 to find the third, and then the second 2 to find the fourth, and so on and so forth. So this means that a sub 3 is equal to the term before it, which is a sub 2, times 2 terms before it, which would be a sub 1. 3 minus 2 is 1. So the second term is 4 times 3, so the third term is 12. And I want to do this one more time. I know I said only to the third term, but I want to do this one more time to make sure that you got it. So a sub 4 is equal to a sub n minus 1, so 4 minus 1 is 3, times 4 minus 2 is 2. So a sub 3 is 12 times a sub 2, is 4, which is 48. Okay? So it says to write a rule for the sequence and then give the next 3 terms. Okay? So I'm not super concerned about the next 3 terms because we just practiced that. What I am more concerned about is, can you write the rule? So here's the thing. We know at bare minimum a sub 1 has to be given for a recursive. It could be a sub 1 and a sub 2. And it's just a matter of guess and check. Some people are really, really good with patterns. Some are not. And it takes a little more practice. So the first thing I always like to try is it just a sub 1 and then like plus or minus a number or times a number. So 4 plus what would be 11? So it'd be 7. But then it's not a constant change. So it's not like plus 7 plus 7 plus 7. So that's not it. So then we have, it's dot subtraction. It's obviously not multiplication because 4 times nothing is 11. So it's not just going to be a simple do this or do this, right? So then it's going to be a matter of, well, it's some combination of operations. So the first thing I'm going to do is just look at this number and think, okay, well, 11 is bigger, so it's probably multiplication, and then it could be addition or subtraction. So it's just a little bit of guess and check. So I would try, how close can I get to 11? So I could do 4 times 2, which is 8, and then I would have to add 3. So then my rule would be a sub n minus 1 times 2 plus 3. So then I would do 11 times 2 is 22 plus 3. That's not it. So then I would do 4 times 3 is 12, and then I would have to subtract 1 to get 11. So then that would be 3 times a sub n minus 1, the term before it, minus 1. So 4 times 3 is 12, minus 1 is 11. So then the next one would be 3 times 11 is 33, minus 1 is 32. So I'm feeling pretty good. 32 times 3 is 96, minus 1, and that's my rule. So a sub n is equal to 3 times the term before it, because that's what that means, minus 1. And order of operations says that we'll do multiplication before addition, subtraction. Okay, so again, at bare minimum, I know it has to give me the first term. So I'm going to try and figure it out based on just the first term. Okay. So of course my go-to is to see if it's a single operation first. Is it just straight subtraction? Which in this case the numbers are getting smaller, so it's obviously either straight subtraction or division. 100 divided by nothing is 60. It'd be a fraction. You could try that. So 100 divided by 60 is 5 over 3. So, or let me rephrase that. So I would be multiplying by 5 over 3. Multiplying by, 3 over 5. So then that would have to mean that 60 times 3 over 5 would have to be 40, and it's not. It's 36. So it's not just straight division or multiplication, however you want to look at it. So then I would try subtraction. Well, 100 minus 40 is 60, which means I'd have to subtract 40 again, which is obviously not right. So then it's kind of, well, we're going to have to try a combination of operations. So if my numbers are getting smaller, I would likely start with division and then add or subtract. So my process, let's see, how close could I get to 60? 100 is evenly divisible by 2, which gives me 50, and then I would have to add 10, and that would give me my 60. So that would mean it's the term before it divided by 2 plus 10. So 100 divided by 2 is 50 plus 10 is 60. 60 divided by 2 is 30 plus 10 is 40. 40 divided by 2 is 20 plus 10 is 30. So that is absolutely my rule. So A sub n is equal to the term before it divided by 2 plus 10. So explicit formulas are easier to use, but students often find it harder to write them because they can be a little more difficult. And students find it easier to find the pattern for recursive but not write the formula. So it's kind of weird how that balances out. So an explicit formula is a rule in which the nth term is defined as a function of n, which means that previous terms are not needed. And this is super convenient. So like if you want to find the 10th term, you just plug in 10. You don't have to find the 9 before it just to find it, which is much, much easier. So a rule in which the nth term is defined as a function of n and previous terms are not needed. Previous terms are not needed. So for example, we're not going to worry about finding the first 5 terms. I only care about the first 3. So a sub 1 means I literally plug in 1. So 7 times 1 minus 3, which would be 7 times negative 2, which is negative 14. A sub 2, going to plug in a 2. So 7 times 2 minus 3 is 7 times negative 1, which is negative 7. A sub 3, 7 times 3 minus 3, which is 7 times 0, which is 0. So it doesn't matter what the equation is, it's the same process. A sub 1, 1/3 to the 1 plus 1, which is 1/3 squared, which is 1 over 9. A sub 2, 1/3 to the 2 plus 1, which is 1/3 cubed, which is 1 over 27. And a sub 3 be 1/3 to the 4th, which is 1 over 81. So number 9, a sub 1, negative 4 to 1 squared, be negative 4 times 1, negative 4. A sub 2, negative 4 times 2 squared, which is negative 4 times 4, negative 16. And a sub 3. Negative 36. So number 10, the only difference is it has 2 n's in it. It makes absolutely no difference. It's just like plugging into any equation you've plugged into since the beginning of time. I have 2 times 1 times 1 plus 5, which is 2 times 4, which is 8. Oh, I subtracted instead of added. I can hear you. I can hear you through the video telling me I did that wrong. It's 12. So a sub 2 is equal to 2 times 2 plus 2 times, or times 2 times 2 plus 5. So that's 4 times 7, which is 28. And a sub 3, 2 times 3 times 3 plus 5 is 6 times 8, which is 48. Okay, so 11 and 12 are the same way. I'll give you the answers and you can plug them in and practice. So a sub 1 is 1, a sub 2 is negative 2, and a sub 3 is 4. For number 12, a sub 1 is 9, a sub 2 is 4, and a sub 3 is 1. Remember, on this video, you can pause wherever you need to. This is on Google Classroom, so you can go back and look at it anytime you need to, okay? So write a rule for each sequence. We're not going to worry about the next 3 terms. We just practice doing the terms. So what I need you to practice is just writing the rule. So here's the thing. Remember, in the last one with their cursive, there was some pattern between this number and this number, this number and this number. But here, there's a pattern between 1 and negative 7, 2 and negative 9, 3 and negative 11, because I have to plug these in. This is my n that I'm plugging in to get those terms, okay? So the convenient thing is I'm always going to check to see if it's linear, because this is always changing by 1. If this is always changing by the same number, then it's a linear equation, which makes it super easy. And in this case, you'll notice that each one of these is changing by a factor of negative 2. So negative 7 minus 2 is a negative 9, minus 2, negative 11, minus 2, negative 13. So that means I just have a linear equation, negative 2n. I just got to figure out what my y-intercept is, and I wouldn't go through the whole figuring out the y-intercept. I would just figure it out from here. Negative 2 times 1 is negative 2, so it has to be minus 5. Negative 2 times 2 is negative 4, minus 5 is 9. Negative 2 times 3 is negative 6, minus 5 is negative 11, so on and so forth. I wouldn't try and figure out the y-intercept the way we typically do with the linear. I would just apply it to the pattern. Okay, so remember again, n is what we're plugging in. So the first thing I'm going to check is there a constant pattern between my output values, my term values, and there's not. So it's a plus 3 and then plus 4 and then plus 7. So that's, plus 5, plus 7, that's not it. Okay, so I have to figure out what is happening to 1 to get 3, and the same thing has to happen to 2 to get 6, 3 to get 11, 4 to get 18, so on and so forth. So you might try multiplication. So is it like times 3? Well, this one works, but this one doesn't. 3 times 3 is 9, not 11. So then I might try something different. Is it times 4 minus 1? So 1 times 4 is 4, minus 1 is 3. 2 times 4 is 8, minus 1 is 7. So that didn't work. So what if it's times 2 plus 1? So times 2 plus 1, times 2 plus 1 doesn't work, because times 2 would be 4 plus 1 would be 5, not 6. So that kind of makes me think that that those are all linear anyway, which you should have known that, but that's not going to work. So it's something that's not linear. So my go-to would be something quadratic. It's obviously not a root because the numbers are getting bigger from my n value, so it's not a root. So I might try quadratic. So what happens if I square this? Well, 1 squared is 1, so I'd have to add 2. So if I do n squared plus 2. 2 squared is 4 plus 2. 3 squared is 9 plus 2. 4 squared is 16. So that's definitely it. Okay. Number 15. So remember, it's a little deceiving. So a sub n is equal to something. And I know there has to be a divide by 2 in there because I have 2 divided by 2's on bottom. So I feel like there's probably a divide by 2. I just got to figure out what's happening. This is definitely not just n divided by 2 because that would be 1/2. So how could I get n? Is it times something? This is bigger than 1, so I feel like it's either times something or add something. But if it was times 2, then the 2's would cancel out, so that's probably not it. So n plus 3. 1 plus 3 is 4 divided by 2 is 2. 2 plus 3 is 5 divided by 2. 3 plus 3 is 6 divided by 2 is 3. 4 plus 3 is 7/2. Okay, just take some guess and check, some just, does this work, does this not work? Okay, add, subtract, multiply, divide, combinations of operations, and so on and so forth. This one, I hope, is a little more obvious. Definitely not linear. Good. So the square root of 1 is 1, square root of 2 is square root of 2, square root of 3 is square root of 3. And then this one may be the one that threw you off because square root of 4 is 2. It's not a radical. It's a perfect square, right? All right, so then we have series. A series is the sum of a sequence. So if it's a finite sequence, you just add the terms. So 4 plus 3 plus 2 plus 1 is 10. If it is if it's an infinite sequence, this one is, obviously these numbers are just getting larger and larger and larger, which means it's going to infinity. This one is a very special one that goes to 1. And I don't need you to worry about it. We will kind of hint at it when we get to geometric, but it is a infinite geometric series, and they're convergent and divergent, which again we don't cover in this class. We'll cover in Algebra 3. So partial sum is denoted with an S sub n, and it just wants you to find the sum of the first, for instance, 9 terms. So clearly I don't have the first 9 terms, but we can find them rather simply. So S sub 9 is literally the sum of 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9, which you can tippity tap in your calculator, and you get that is 45. Tedious, I am aware, but necessary. So S sub 4, much nicer to work with. S sub 4 is 4 plus 7 plus 13 plus 25. The sum of the first 4 terms. Okay, so number 3. S sub 6, I don't have the first 6 terms. I got 1, 2, 3, 4, 5. I need one more, so I need to know what the pattern is. So I have plus 3 plus 5. So that's not it. Because then that's plus 7. That's plus 9. So then my next one would be plus 11, which would be 36. It's also perfect squares. 1 squared, 2 squared, 3, 4, 5, and 6. So depends on how you see it, I suppose. So S sub 6 would be equal to 1 plus 4 plus 9 plus 16 plus 25 plus 36. Which is equal to 91. So S sub 3, we have the first three terms, 1 plus 1/2 plus 1/3. So S sub 3 11/6. So the last thing is summation notation. It's a way to represent a series using the Greek letter sigma to denote the sum. So this is not an E, it's called sigma. Okay, where the top number is the last term number, the bottom is the first term number, and this is the formula for the sequence, and it is explicit, meaning I'm going to plug in these numbers, right? So if I want to find the sum of the series that's above, that means I'm going to start with 1. So 2 times 1 plus sum, right? 2 times 2, all the way up to 2 times 5, because it's the last term value, which is 30. Okay. So expand each series and evaluate. So 1 to 12, that's a little much to start off with. So let's just go to number 6. 1 to 7, much more reasonable. So we have -3 times 1 plus -3 times 2 plus -3 times 3, all the way up to -3 times 7. So that's how I expand. And then we can evaluate. So -3 plus -6 plus -9 plus -12 minus 15 minus 18 minus 21. So my sum is equal to -84. Okay, so number 7, so the same thing. It says I start at 1 and stop at 4. So 5 times 1 plus 2 plus 5 times 1, or 5 times 2 plus 2 plus 5 times 3 plus 2 plus 5 times 4 plus 2. So 5 times 1 is 5 plus 2 is 7 plus 5 times 2 is 10 plus 2 is 12. 15 plus 2 is 17. And 22, and then add them all up, and you get 58. Okay, so number 8 is a little bit different. Because notice we don't start with 1, we start with 2 and we go to 9. So that would be 2 times 2 minus 7 plus 2 times 3 minus 7, 2 times 4 minus 7, 2 times 5 minus 7, 6 minus 7, all the way up to 2 times 9 minus 7. Very tedious, I'm aware. Whining and complaining will not change that, yes, we have to do this. So you have 4 minus 7, which is negative 3. 6 minus 7, negative 1. 8 minus 7 is positive 1. 10 minus 7 is positive 3. 12 minus 7 is 5. 14 minus 7 is 7. 16 minus 7 is 9. And 18 minus 7 is 11, which gives us 32. Okay, it doesn't really matter what the pattern is. You follow order of operations. So let's look at number 12. So this has kind of a little bit of everything. It's not linear. It doesn't start at 1 and then has a multiplier of 3 on the outside. So that means I'm going to have 3 times my pattern. So I start with 4. So 4 minus 4 squared plus 5 minus 4. Oh, sorry. I got my pattern wrong. 4 minus 5 squared plus 4 minus 6 squared plus 4 minus 7 squared plus 4 minus 8 squared. So I have 3 times 0 squared plus negative 1 squared plus negative 2, so I'm going to let you finish. Negative 2 squared plus negative 3 squared. Negative 4 squared. So that gives me 3 times 30, which is 90. Okay? So for homework on page 3, I would like you to do number 1, number 4, find only the first 3 terms, 5, 6, 7, first 3 terms, 8, 11, 12, 15, 19, and 22. So I'm going to write that out for you. So page 3, 1, 4, 5, 6, 7, 8, 11, 12, 15, 19, and 22. That's what I want you to do for homework.